Section 7.2, Rational Functions and their Graphs. In this section we will discuss what is a rational function, determine the domain of a rational function, then we'll learn how to find various asymptotes of a rational function, including vertical, horizontal, and oblique asymptotes. We'll use all that information to learn how to sketch the graph of a rational function and determine where any holes in the graph of a rational function occur. We'll see an application, and then we'll kind of turn the idea around and see how we can take a graph and from that determine a rational function that models that graph. A rational function is a quotient of polynomial functions. That is, f of x equals p of x over q of x is a rational function, where p of x and q of x are polynomials and q of x is non-zero. Now, since division by zero is undefined, the domain of a rational function is the set of all real numbers except those values of x that would yield a zero denominator. So let's see some examples where we're asked to determine the domain of a rational function. For example, we have f of x is equal to 7 over x squared. Notice that if I take the denominator x squared and set it equal to 0, x squared equals 0 only if x equals 0. So therefore, this tells me that when x is 0, the denominator is 0. So the domain of this function is the set of numbers x such that x is not equal to 0. And what this says is any other number is a valid input for this function except 0. We could also write this using interval notation as negative infinity to 0 parenthesis union 0 to infinity. Let's look at the second example. Here we have f of x is x cubed minus 3x plus 1 over x minus 9. Notice that x minus 9 equals 0 implies that x equals 9. So if x is 9, the denominator takes the value 0, and we would have division by 0, which is undefined. So then the domain of this function is the set of x such that x is not equal to 9. And again, we could write that as using interval notation, negative infinity, comma 9, union 9, comma infinity. In our third example, we have f of x is 2x plus 5 over x squared minus 9. So notice that x squared minus 9 equals 0. Well, I can factor that as x plus 3 by x minus 3. And then if I set each factor to 0, x plus 3 equals 0, which implies that x equals negative 3. Or x minus 3 equals 0, which implies that x equals positive 3. So if x takes either of those values, the denominator becomes 0, resulting in an undefined expression. So for our domain, we would have the set of numbers x such that x is not equal to negative 3 or 3. And again, we could write this using interval notation. We would go from negative infinity to negative 3, union negative 3 to 3, union 3 to infinity. All right, so there's some examples of finding domain of a rational function. All right, so now we're going to use a calculator to help us look at the graph of f of x equals 3x minus 5 over x minus 2. Now, something we already know is that if I were to set the x minus 2 equal to 0, that implies that x equals 2. So then my domain is x such that x cannot equal 2. Alright, so let's bring up the calculator now. Let's look at the graph of this function, and let's see what happens at x equals 2. Alright, so my y equals screen, I have 3x minus 5 over x minus 2. Notice how I'm using parentheses around the numerator and denominator. And let me check my window. Let me just go to the standard window for now. So negative 10 to 10 by 1s, negative 10 to 10 by 1s. And I'll graph it. And notice that there's something interesting here, right in the middle of the graph. And it appears to be pretty close to x equals 2. I'm going to adjust my window slightly to negative 9.4 on the x minimum and 9.4 on the x maximum. I'm doing that because of the number of pixels that there are in the window for the calculator, and it turns out that these numbers work well when graphing. And so notice that that feature disappeared. And we see that that interesting feature is happening. It appears to be pretty close to x equals 2. And in fact, what we call that feature is a vertical asymptote. Alright, so I've transferred the graph over to our screen. And what happens is we have this feature called a vertical asymptote, which I'm drawing in with this dotted line at x equals 2. So we have a vertical asymptote at x equals 2. Now, when we draw these by hand, what we will draw is that the curve gets very close to the asymptote and continues downward along the asymptote. And then coming from the right, on the right-hand side, it's moving up and approaching the asymptote. But it never actually touches the asymptote. It can't, because if x was 2, there would need to be a point at x equals 2. But we know that when x equals 2, that's outside the domain of this function, and it's an undefined expression when x equals 2. So we can't get a point on the curve when x equals 2. So when do we expect vertical asymptotes? If f of x equals p over x is a rational function, and p of x and q of x have no common factors, so that fraction is in its reduced form, there are no common factors between the numerator and denominator, then the line x equals k is a vertical asymptote of the graph of the function if q of k is 0. So if k is some number that makes the denominator 0, then we expect a vertical asymptote when x equals k. Of course, the function must be in its reduced form. The graph of the function cannot cross any vertical asymptotes. Alright, so let's see some examples where we're just trying to find vertical asymptotes, if any. Alright, so we have the function f of x equals x squared minus 3 over 3x minus 1. So notice that 3x minus 1 equals 0. Add 1, divide by 3 implies that x equals 1/3. Now, can I factor the numerator? Well, I could if I really wanted to, as x plus the square root of 3 and x minus the square root of 3. I haven't really done much like that. I could factor it like that, but it's not going to reduce with anything in the denominator. So what that means is this is reduced, right? There are no common factors between numerator and denominator. And what we know is that x equals 1/3 makes the denominator equal to 0. So, what that tells me is there will be a vertical asymptote at x equals 1/3. All right, so for that function, I expect a vertical asymptote at x equals 1/3. All right, second example. We have f of x is x minus 7 over x squared minus 4. Now, I can write the denominator as x plus 2 by x minus 2. Notice that there are no common factors between the numerator and denominator. So what that tells me is, setting the denominator to 0, I'd have x plus 2 times x minus 2 equals 0. Setting each of the factors to 0, x plus 2 equals 0, which implies that x equals negative 2. X minus 2 equals 0, which implies that x equals positive 2. I can't remove either of those factors with the numerator, so I expect that there are vertical asymptotes at x equals negative 2 and x equals positive 2. And we can have more than one vertical asymptote in the graph of a rational function. In the third example, we have f of x is negative 7x over x squared plus 9. Now, I don't know, we haven't learned how to factor x squared plus 9 in this course. And in fact, if we tried our other method, x squared plus 9 equals 0, and subtracting 9, we'd have x squared equals negative 9, and then using square root property, we'd have x is equal to plus or minus 3i, because we're taking the square root of a negative number. So those are non-real. So positive 3i, negative 3i, those don't show up on the graph of this function using real numbers. So this function has no vertical asymptotes. There are no real values of x that make the denominator equal to 0. All right, let's go back to that graph and take another look at it. Notice that as x becomes very large, either positive or negative, we appear to get almost a horizontal line. And that horizontal line appears to be pretty close to, let's see, 1, 2, it appears to be pretty close to y equals 3. The graph is getting very close to that value of 3. And so you might want to know, well, when does this happen? And if it does happen, can we determine the value of this horizontal asymptote? In this case, the horizontal asymptote is at y equals 3. So we want to be able to figure out when this will happen, when we'll see this feature, and if we will see this feature, where will it happen? All right, so horizontal asymptote, a little bit more complicated than the vertical asymptote. All right, so if we have a rational function, the line y equals k is a horizontal asymptote of the graph of the function if the function approaches that k value, that y value, as x approaches negative infinity or x approaches positive infinity. So if we're far to the left on the graph and far to the right on the graph, and we get closer and closer to this k value, we say y equals k is a horizontal asymptote. Now, unlike vertical asymptotes, the graph of the function can cross the horizontal asymptote. Alright, so here's how we determine if we will have a horizontal asymptote for a rational function. Alright, so we have our function as p of x over q of x, polynomials. And so what I've done is I've written out the expanded polynomial for our numerator and expanded polynomial for the denominator. And really what we kind of want to focus on are the lead terms. We have a sub m x to the m, that's the lead term in the numerator, and b sub n x to the n, that's the lead term in the denominator. And so m is the degree of the numerator, n is the degree of the denominator. And so now we get three cases. If m is less than n, alright, so what does that mean? If the degree of the numerator is less than the degree of the denominator. Alright, so this is the first case. If the degree of the numerator is less than the degree of the denominator, then the line y equals 0. The x-axis is the horizontal asymptote of the function. Okay, so basically what happens in that situation is the denominator has a higher degree and eventually overtakes any values in the numerator. And so we are dividing by larger and larger numbers, and that drives to 0. If m equals n, if the degrees are equal, right, if the degree of the numerator is equal to the degree of the denominator, then the line y equals a sub m over b sub n is the horizontal asymptote. A sub m over b sub n. So those are the lead coefficients of the numerator and denominator respectively. So if we have equal degrees, then we have the line y equals, we take the ratio of the lead coefficients, and that would give us our horizontal asymptote. If m is greater than n, if the degree of the numerator is greater than the degree of the denominator, we do not get a horizontal asymptote. Okay, because eventually the numerator is having much larger values than the denominator, and so that goes to very large numbers, infinities, negative infinities. Alright, so let's see some examples. Find the horizontal asymptote if it exists. So here we have the function f of x is x squared minus 3 over 3x minus 1. So let's look at the degrees. The numerator has degree 2. The denominator has degree 1. Since the degree of the numerator is greater than the degree of the denominator, this graph will have no horizontal asymptote. Let's look at the second example. F of x is 6x minus 7 over x squared minus 4. Let's take into account the degrees. The degree of the numerator is 1. The degree of the denominator is 2. Since the degree of the numerator is less than the degree of the denominator, we will have a horizontal asymptote at y equals 0. Third example. We have the function f of x is the opposite of 7x squared over 4x squared plus 9. Now, I can write that if I want as negative 7x squared over 4x squared plus 9. I just basically took the negative and put it in the numerator. Notice that the degree of the numerator is 2, and the degree of the denominator is also 2. Since the degrees are equal, then I will have a horizontal asymptote at y equals. Now I take the ratio of the lead coefficients. So I have a -7 in the numerator, and I have a 4 in the denominator. So y at y equals -7/4. All right, so that's how we find horizontal asymptotes for rational functions. Now, the graph of a rational function can possibly cross its horizontal asymptote. Let's see an example and determine if it will happen for this example. Determine if the graph of f of x equals 5x squared minus 3 over x squared minus 8 will cross its horizontal asymptote. Alright, so first we have to define where the horizontal asymptote occurs, if it occurs. So notice that we have a degree 2 over degree 2, so we will get a horizontal asymptote. We take the ratio of the lead coefficients, 5 and 1. So we would have a horizontal asymptote at y equals 5 over 1, or y equals 5. So we know we have a horizontal asymptote. Now, to determine if the graph will actually cross the horizontal asymptote, we take the function, we need to now solve, will the function equal 5? So will 5x squared minus 3 over x squared minus 8 equal 5? Now to solve this equation, we multiply through by the denominator, x squared minus 8. So that reduces out on the left-hand side, leaving 5x squared minus 3. On the right-hand side, I'd have 5x squared minus 40. Now, if I subtract the 5x squared from both sides, I get the statement that -3 equals -40, which is a contradiction. So what that tells me is the equation has no solution. And so therefore, the graph of the function will not cross its horizontal asymptote. If we had solved that equation and gotten real values, real x values as solutions, then we would have places where it crosses the asymptote. Alright, so let's consider the graph of f of x is x squared minus 3x minus 4 over x minus 1. What do we expect regarding asymptotes? Well, if we factored the numerator, we would have, that factors as what, x plus 1 by x minus 4 over x minus 1. There's no common factors between the numerator and denominator. We expect a vertical asymptote at x equals 1. What about the horizontal asymptote? Well, we have a degree 2 over degree 1. So since the degree of the numerator is greater than the degree of the denominator, there's no horizontal asymptote. Alright, so now I'm going to graph this function on the calculator and see what happens. Alright, so x squared minus 3x minus 4, x squared minus 3x minus 4, and we're dividing that by x minus 1. Alright, so let me graph this. Now I'm using the window -9.4 to 9.4 on the x's, -10 to 10 on the y's. Alright, so we do see a vertical asymptote, and it appears to be at x equals 1. Alright, and I brought the graph down. So it does appear that we have the vertical asymptote at x equals 1. That seems reasonable. Nothing new there. And there's no horizontal asymptote, as we expected. But notice that as x becomes large, there appears to be a slant asymptote, or what's called a slant or an oblique asymptote. So notice that as x becomes large, the graph appears to follow that line that I just drew in red. There's an oblique asymptote. So where is this coming from? Alright, so I'm going to take that function and I'm going to show you where that oblique asymptote comes from. I'm going to use long division. Actually, since I'm dividing by x minus 1, I'm going to use a synthetic division. So let me divide 1 into x squared minus 3x minus 4. Long division, drop the 1, multiply. It's 1, add is negative 2, multiply negative 2, negative 6. So what that tells me is x squared minus 3x minus 4 over x minus 1 is x minus 2, and then we have a remainder term of negative 6 over x minus 1. Now, let me go back to the calculator, and I've got that, my function still up there. Now I'm going to graph y equals x minus 2. Let me graph y equals x minus 2. And notice that y equals x minus 2 appears to model that oblique asymptote. So this part, the quotient, right, the quotient yields the oblique or slant asymptote. Alright, so let's formalize this. Let f of x equal p of x over d of x be a rational function in lowest form, such that the degree of p of x, the degree of the numerator, is exactly 1 more than the degree of d of x, the denominator. If the numerator is of degree exactly 1 more than the degree of the denominator, then the graph of the function will have an oblique or slant asymptote. To find that oblique asymptote, we divide p of x by d of x, where the quotient is q of x, and the remainder is r of x. Since the degree of p of x is 1 more than the degree of d of x, the quotient is a linear function, which will be the oblique asymptote of f of x. Alright, so as I showed in the previous example, I went through the division process. I was able to use synthetic division since I was dividing by a linear factor. And I used that division process. The quotient yielded the oblique asymptote. Now that we've talked about some of the features of the graph of a rational function, let's actually get some examples in of sketching these graphs by hand. And here are some guidelines. We want to determine the domain of the function. We've seen how to do that. We want to be able to determine any intercepts. We've talked about how to find intercepts for other functions, and the process is similar for this function. To find the y-intercept, you set x to 0. To find any x-intercepts, you set y to 0 and solve the resulting equation. We're going to determine any asymptotes. We've seen how to do that in this section. We will use dashed lines to denote any asymptotes. We're going to check to see if the graph will cross the horizontal asymptote, if there is one. Then we're going to plot a few other points between and beyond any x-intercepts and any vertical asymptotes to help us get more of a guide of the curve. And then we'll sketch the curve using the asymptotes and points you have plotted as guides. Alright, so here's an example. We're going to sketch without a calculator f of x equals 2x over x minus 3. First thing I'm going to do is determine the domain. Alright, so notice that if I set the denominator equal to 0, that gives me x equals 3, and I can't reduce anything from the numerator, so the domain is x such that x cannot equal 3. y-intercepts. Let's find the y-intercept. F of 0. That would be 2 times 0 over 0 minus 3. And that's going to be 0 over negative 3, which is 0. So the y-intercept is the origin, 0, 0. Now to find x-intercepts, we would set the function equal to 0. 2x over x minus 3 equals 0. Now if I multiply through both sides by x minus 3, I get 2x equals 0, which implies that x equals 0. So I didn't get any new information. All I still know is that it passes through the origin. All right, so I have the domain, I have the intercepts. Asymptotes. All right, well, I know that I can't factor the numerator, so I expect a vertical asymptote at x equals 3. What about is there a horizontal asymptote? Let's look at the degrees. We have a degree 1 over degree 1. So yes, I will get a horizontal asymptote at y equals the ratio of the lead coefficients. So that would be 2 over 1. So at y equals 2. All right, so let me draw in my vertical asymptotes. My vertical asymptote at x equals 3, and I'm going to draw these in red, the asymptotes. So at x equals 3, I have a vertical asymptote. And at y equals 2, I have a vertical asymptote. And all I know so far is that the curve passes through the origin at 0, 0. So I need at least, I'm going to find at least 1, 2, 3 other points. I want a point that's to the left of 0, a point between, to the left of x equals 0. I want a point between x equals 0 and x equals 3, and I want a point to the right of x equals 3. So how about f of negative 5? How about negative 5? Well, that would be 2 times negative 5. That would be negative 10 over negative 5 minus 3. That would be negative 8. So that would be 1 2/8. That would be 1.25. So f of negative 5 is 1.25. So that's about here. Oh, and I didn't, go back to asymptotes. I didn't check something. Will the function cross its horizontal asymptote? Will 2x over x minus 3 ever equal 2? Multiplying through by x minus 3, I find that 2x equals 2x minus 6, which implies that 0 equals negative 6. That's a contradiction. Okay? Does not cross. All right, back over here, I found that f of negative 5 was 1.25. All right, how about a point between 0 and 3? Let's evaluate f of 2. F of 2 would be 2 times 2, that's 4, over 2 minus 3 is negative 1, that's negative 4. F of 2 is negative 4. And a point to the right of x equals 3. How about when x is 5? F of 5 would be 2 times 5, that's 10, over 5 minus 3 is 2. F of 5 is 5. All right, so now thinking about the curve, we know that it has this horizontal asymptote. So as I'm far to the left, I'm approaching y equals 2. Now if I look at these points in the middle, right, if I look at these points on the curve, they suggest that I'm approaching this horizontal asymptote from below, and I'm getting closer and closer. Right, then the curve, now thinking from left to right, I'm asymptotic at y equals 2, and then I pass through the origin. That's my only intercept. I'm going to pass through the point 2, negative 4, and I know I cannot cross over the vertical asymptote, so I must get closer and closer and closer to it. Now, on the right-hand side, I know that I must approach the horizontal asymptote again. So from my point at 5, 5, I must get closer and closer, something like that. And I know I must approach and get closer to the vertical asymptote, so something like that. And so there's a sketch of the curve. Alright, here's another example. Sketch without a calculator. F of x is x squared plus 5x plus 4 over x squared minus 4. Alright, let's first determine the domain of the function. Well, I think I can factor this. So let's see, x squared plus 5x plus 4 factors as x plus 1 by x plus 4. The denominator, x squared minus 4, factors as, what does it factor as? It factors as x plus 2 by x minus 2. So the domain, setting the denominator to 0, I can't have x plus 2 equals 0, so that means x equals negative 2. I can't have x minus 2 equals 0, so that means that x equals 2. So for my domain, we have the set of x such that x is not equal to negative 2 or 2. Intercepts. F of 0 would be 0 squared plus 5 times 0 plus 4 over 0 squared minus 4. So that would be 4 over negative 4. That would be negative 1. So I have a y-intercept of 0, negative 1. Setting the function equal to 0 to find any x-intercepts, I'd have, now I'm going to use the factored form here. If I have x plus 1 by x plus 4 over x plus 2 by x minus 2 equal to 0, well, a fraction can only equal 0 if the numerator equals 0. So that tells me that x plus 1 times x plus 4 equals 0, which implies that x plus 1 equals 0, x equals negative 1, x plus 4 equals 0, x equals negative 4. So I have two x-intercepts at negative 1, 0 and negative 4, 0. Asymptotes. Well, I can't remove any factors between the numerator and denominator, so I'm expecting vertical asymptotes at x equals negative 2 and x equals positive 2. Looking at the degrees of the numerator and denominator, I have a degree 2 over degree 2. So since they're the same, I get a horizontal asymptote at y equals, now taking the lead coefficients, 1 over 1, at y equals 1 over 1, at y equals 1. Will the function ever cross its vertical asymptote? Alright, so can x squared plus 5x plus 4 over x squared minus 4 ever equal 1? Well, if I multiply through by the denominator, by x squared minus 4, then I would have x squared plus 5x plus 4 equals x squared minus 4. So notice those x squares are going to reduce out, or are going to subtract out. And so now I have a linear equation, 5x plus 4 equals negative 4. I'm going to subtract 4 from both sides. 5x equals negative 8, and divide through by 5, and x equals negative 8/5. So I
can cross the horizontal asymptote, all right, and we'll cross the horizontal asymptote at -8/5, comma 1. So the curve does cross the horizontal asymptote at that point, -8/5, comma 1. All right, so let's draw in the asymptotes in red. Let's see, we have x equals -2. I don't like that line. Let's try that again. X equals +2. And at y equals 1. Let's plot the points we know. We have a y-intercept at 0, -1. We have an x-intercept at -1, 0, and at -4, 0. We also know that we cross the horizontal asymptote at -8/5, comma 1. -8/5, that's -1 and 3/5, so that's about here. So already I have a pretty good idea of the curve. I know as I move far to the left, I must get close to this horizontal asymptote. And so considering I have the point -4, 0, that suggests that I have to do something like this. And I have to get close to the horizontal asymptote. Now, in between the horizontal asymptotes, I see those 3 points, and they suggest that I'm going to have to do something like this. Now, I could plot another point, maybe, to be sure what happens when x equals 1. So the question is, does it do this, or does it turn back over and do this? Well, it can't turn back over, because if it turned back over, I would have had another place where the curve crossed the horizontal asymptote. So I know it must trend downward. Alright, so I really need to now only figure out one more spot. What happens when x is greater than 2? So let's let x equal, how about 4? Let's evaluate f of 4 and see what happens. F of 4, doesn't matter which form you use. Let's see, I'll use 4 squared, that's 16. 5 times 4 is 20, plus 4, over 16 minus 4. So let's see, that's 36, that's 40. Over 16 minus 4 is 12. And so 40 over 12, let's reduce that by 4. That's what, 10 over 3, that's 3 1/3. So f of 4 is 3 1/3. So we have this point here. Alright, so now we know the curve doesn't cross over its horizontal asymptote again, so it must follow the asymptotes and do something like this. And there's the graph of the function. Now let's sketch without a calculator. F of x is x squared plus 8x minus 1 over x plus 1. Alright, so let's think about this. Domain. X cannot equal -1, setting the denominator to 0. Alright, intercepts. F of 0 would be -1 over 1, which is -1. So we have 0, -1. Can there be x-intercepts? Can x squared plus 8x minus 1 over x plus 1 equal 0? Well, that can only happen if the numerator can equal 0. X squared plus 8x minus 1 equals 0. I'll apply the quadratic formula. X would equal -8 plus or minus the square root of 64 minus 4ac, so that's plus 4 over 2a is 2. So that's negative 8 plus or minus the square root of 68 over 2. So that's negative 8 plus or minus, now reducing that radical, the square root of 68, that's 4 times 17. So that's 2 root 17. 8 plus or minus 2 root 17 over 2. And so x is negative 4 plus or minus the square root of 17. So there are two x-intercepts at negative 4 plus or minus the square root of 17. All right, so we have domain and we have intercepts. Asymptotes. Well, we have an asymptote at x equals negative 1. I should have said for the domain that's x such that x cannot equal negative 1. Sorry about that. For asymptotes, we have a vertical asymptote when x is negative 1. Horizontal asymptote. Well, we have degree 2 over degree 1. None. But since the degree of the numerator is exactly 1 more than the degree of the denominator, we expect a slant or an oblique asymptote. So I'll use long division. No, I'll use synthetic division. Negative 1, 1, 8, negative 1, dividing. 1 times negative 1 is negative 1. 7 times negative 1 is negative 7, so that's a negative 8. So I expect a slant asymptote, or an oblique asymptote, at y equals x plus 7. Alright, so let's draw in what we have so far. I have a vertical asymptote at x equals negative 1. I'll just use a scale of 1s here. So there's my vertical asymptote. I have an oblique asymptote at y equals x plus 7. So that's a slope of 1 and a y-intercept of 7. 1, 2, 3, 4, 5, 6, 7. And a slope of 1. Alright, so I'm just using the slope of 1 repeatedly. Alright. So there's my oblique asymptote. That's going to continue on. What do we have? What else? I have an intercept at 0, negative 1. And I have x-intercepts at negative 4 plus or minus the square root of 17. So square root of 17 is a little bit more than 4. Let's say that's approximately, I don't know, 4.1, 4.2. Let's just say it's about 4.1. So then negative 4 minus 4.1 is negative 8.1. So I have an x-intercept at about negative 8.10. So 1, 2, 3, 4, 5, 6, 7, there's negative 8.10. And negative 4 plus 4.1, I have an x-intercept at approximately 0.1, 0. All right, now let's get a couple other points to help us out. How about let's find a point somewhere in this range, in this interval. So somewhere between negative 7 and negative 1. Let's evaluate what is f of, how about negative 2? Alright, so substituting into the function. That would be negative 2 squared, that's 4. 8 times negative 2, that's a minus 16 minus 1. And negative 2 plus 1. Alright, so that is 4 minus 16 minus 1, that's negative 12, that's negative 13 over negative 1, that's 13. So I have the point negative 2, 13. So that's a point that's like up here somewhere. So now, sort of following the shape and the asymptotes, I've got a feeling that the curve will follow this asymptote the slant asymptote passes through the intercept and then curves upwards and hits that point and follows the vertical asymptote. Alright, how about a point that's further to the right of our last x-intercept? So how about when x equals 2? What's f of 2? F of 2 would be 2 squared, that's 4, plus 8 times 2 plus 16 minus 1 over 2 plus 1. That's 20 minus 1, that's 19 over 3. So that's what, 6 1/3. So we have the point 2, 6 1/3. 1, 2, 3, 4, 5, 6 1/3. So there's that point. So following the shape of the curve, we know it cannot cross the vertical asymptote. So it's going to come up, pass through 0, -1, pass through the x-intercept, pass through this point 2, 6 1/3, and follow the slant asymptote. So there's a sketch of the curve without a calculator. Alright, here's another example. Our function is 2x squared minus x minus 3 over x minus 4. Again, for the domain, setting the denominator to 0, we'd have x such that x cannot equal 4. Intercepts. The y-intercept, f of 0, would be -3 over -4, so that's 3/4. So we have 0 3/4. Setting the function to 0, 2x squared minus x minus 3 over x minus 4 equals 0. That would imply the numerator, 2x squared minus x minus 3 equals 0. And this, you could use the quadratic formula again like I did in the previous exercise, but this, I think, factors. Let's see, we'd have an x and a 2x. I'd have to have a 3 here and a 1 here. Plus, minus. I think that works. X plus 1 by 2x minus 3 is 0. So x plus 1 equals 0, x equals -1. 2x minus 3 equals 0, x equals 3/2. So I have two x-intercepts at -1 and at positive 3/2. Asymptotes. Now since the numerator factors, so I can write this, what, x plus 1 by 2x minus 3 over x minus 4, nothing reduces, so I do expect a vertical asymptote at x equals 4. Can we find a horizontal asymptote? Well, again, we have a degree 2 over a degree 1, so no horizontal asymptote. But notice the degree of the numerator is exactly one more than the degree of the denominator. So I can again use synthetic division here. So let me divide the 4 into 2x squared minus x minus 3. Bring down the 2 and multiply. That's an 8. That's a 7, 28, 25. So then I have a oblique asymptote at y equals 2x plus 7. Alright, so let's plot what we have so far. I have my vertical asymptote at x equals 4, and I'll just go ahead and use the same scale by ones. So there's my vertical asymptote at x equals 4. I have no horizontal, but I have an oblique asymptote at y equals 2x plus 7. And we have a slope of 2. Alright, so there's a couple of points on the line, and I guess let me extend this vertical asymptote upwards. Alright, let's plot what we have. I have a y-intercept at 0 3/4. I have x-intercepts at -1 and at 3/2. Alright, so I have a pretty good idea of what's going to happen in between the asymptotes. It looks like I'm going to get something like this. And I could plot a couple extra points. And then what happens on the other side? Well, it's probably going to fit in the, in between them, but let's just double check. It's probably the rest of the curve is probably in between those asymptotes. Let's just double check. How about let's let x equal 5. What's f of 5? F of 5 would be 2 times 5 squared. That's 2 times 25. That's 50 minus 5 minus 3 over 5 minus 4. So 50 minus 5 minus 3, that's 42 over 1. That's 42. F of 5 is 42. So I probably should have used a different scale. I've got a point that's way up here somewhere. Well, about f of 6. F of 6 would be 2 times 36. That's 72 minus 6 minus 3 over 6 minus 2. So that's 63 over 6 minus 4 is 2. That's about what, 31.5. So up here, and so let me redraw this. I need to redraw this on a different scale to show the curve correctly. Alright, so let's use a scale of I'm going to use a scale of 5 on the y-axis. Alright, so let's change this. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50 on the y-axis. I'm going to leave the x-axis alone. Alright, so x equals 4. Still right here. That's my vertical asymptote. Now I've got y equals 2x plus 7. So now 7 is here. And a slope of 7 is here. Alright, so 7 is here. And I have a slope of 2. So now that curve would look, or that asymptote, that slant asymptote would look more like this on this scale that we have. Alright, now plotting the points that we have. X is -1 is an intercept. 0, 3/4 is an intercept. And 3/2, 0 is an intercept. Alright, so we still expect the curve to do roughly this. Now we have a couple of other points. We have f of 5 is 42. So f of 5 is 42. That's about here. F of 6 is 31.5. Alright, so now I'm expecting the curve to do something like this. Alright, so there's a rough sketch of the curve without a calculator. Alright, one more example. We have x cubed plus 4x squared minus 3x minus 12 over x squared plus x minus 12. Ooh, let's look at this and let's see if we can do any factoring. X cubed plus 4x squared minus 3x minus 12. That's x squared times x plus 4 minus 3 times x plus 4. So that's x squared minus 3 by x plus 4. In the denominator, x squared plus x minus 12, that factors as x plus 4 by x minus 3. So notice that we have a common factor of x plus 4. Alright, so g of x is x squared minus 3 over x minus 3, where x is not equal to negative 4. I'm reducing that factor out, but I have to say x cannot equal negative 4. And in fact, we will have a whole at g of negative 4 is 16 minus 3 over negative 4 minus 3. That's 13 over negative 7, negative 13 sevenths. So we have a whole at negative 4, negative 13 sevenths. Alright, so let's remember that. Alright, now working with g of x, we would now expect a, let's see, what's my y-intercept? At, that would be at f, at g of 0 would be 0 minus 3, negative 3 over negative 3, that's 1, at 0, 1. X-intercepts, setting x squared minus 3 to 0, that implies that x squared equals 3, so x is plus or minus the square root of 3. So we do have two x-intercepts, negative root 3, 0, and positive root 3, 0. Asymptotes, we would have a vertical asymptote at x equals 3. That makes the denominator 0. Horizontal asymptote, none, because we have degree 2 over degree 1. We do expect a slant asymptote. Using synthetic division, we'd have 3 dividing into, let's see, we'd have 1, 0, negative 3. So that's 1, 3, 3, 9, 6. So we have a slant, or an oblique asymptote, at y equals x plus 3. Alright, so let's plot what we know. We have a vertical asymptote at x equals 3. I'll start with a standard window, a standard scale of 1s. And y equals x plus 3, 2, 3, and a slope of 1. So drawing this with a slope of 1. Plotting the points that we know. We have a y-intercept of 0, 1. We have x-intercepts at negative root 3 and positive root 3. The square root of 3 is approximately 1.7. So negative root 3 and positive root 3. We have a whole at negative 4, negative 13 sevenths. Negative 1, negative 2, negative 3, negative 4, negative 13 sevenths. So negative 13 sevenths is 1 and 6 sevenths. That's about here. 1 and 6 sevenths is there. Alright, and drawing the curve, we follow the asymptote, pass over the whole, go through the points we are aware of, and it's got to approach the asymptote. Now if we plot a couple other points, I've run out of room here, so I'll work back up here at the top. Let's see, f of 3, how about f of 4? F of 4, let me use g. Sorry, g of 4 would be 16 minus 3, that's 13, over 4 minus 3 is 1. G of 4 is 13 over 1 is 13. So we have the point 4, 13. There's 10, 11, 12, 13 would be about here. Let's get another point. How about when 6? G of 6 would be 36 minus 3, that's 33, over 6 minus 3 is 3, that's 11. So g of 6 is 11, so that's about here. So it looks like the curve is going to do something like this. Alright, and so there's a sketch of the curve. Alright, so now that we've seen how to graph a couple of them, let's consider another example. Here we have x squared minus 6x plus 8 over x minus 2. So we know that if x minus 2 equals 0, that implies that x equals 2. So we know for the domain that x cannot equal 2. And, well, should we expect a vertical asymptote at x equals 2? Alright, so let's see the graph of this function. Y equals, let me clear that out. Let's see what we have, x squared minus 6x plus 8. Close that off and divide by quantity x minus 2. And let's see what this graph looks like. Alright, so when I graph it, I get a line. I don't get a vertical asymptote at x equals 2. Now, if you look really close, let me see if I can blow this up a little bit. If you look really close at the graph, you see right here, when x equals 2, notice it kind of skipped a point there. Let me try to trace and get close to 2. When I trace, let's see what happens when I trace and get to 2. I'm at x equals 1.8. If I go one space over, look what happened. When x equals 2, I get nothing here for the output. Well, of course not, because the function is undefined when x equals 2. But notice that there's no asymptote there. Instead, there's just this space. There's this hole in the graph. Alright, now let's see why that happened. Notice that I could have written x squared minus 6x plus 8 as x minus 2 by x minus 4. That's its factored form. And the denominator is x minus 2. Now, I know that the domain is x cannot equal 2. Now, I'm allowed to remove the factor of x minus 2, but I have to remember that x cannot equal 2. So, we have a new function call it g of x. G of x, I remove the factor of x minus 2. G of x is x minus 4, where x cannot equal 2. So now notice 2, right? So notice that g of 2, if it existed, would be 2 minus 4, which is negative 2. And notice, and when we go back to the graph, notice that this y value, that this hole, appears to be near 2, negative 2. In fact, let me put in a value that's very close to 2. How about 1.999? When x is 1.999, the y value is pretty darn close to negative 2, isn't it? Alright, so we get a hole. We have this new function, g of x is x minus 4, where x is not equal to 2, and the function g of x has a hole at 2, negative 2. Alright, so when do we find holes in the graph of a rational function? If x minus k is a factor of both the numerator and denominator of a rational function, then there will be a hole in the graph of f of x at x equals k. To determine the full coordinates of the whole, substitute x equals k into the reduced form of the function. Alright, so let's see this example. We're going to sketch f of x as x squared minus x minus 2 over x squared minus 2x minus 3. Now, the first thing I'm going to do with this is factor it. The numerator factors as x plus 1 by x minus 2. The denominator factors as x plus 1 by x minus 3. So, what does this tell me? Since I see that I have this common factor of x plus 1 in the numerator and denominator, then I will write g of x is x minus 2 over x minus 3, where there is a whole at x equals negative 1. Going further, g of negative 1 would be negative 1 minus 2 over negative 1 minus 3. That would be negative 3 over negative 4, 3/4. So there is a whole at negative 1, 3/4. Alright, so I'm going to draw that hole in right away. There's that hole at negative 1, 3/4. Now, to figure out the rest of the graph, I work with my new function, g of x is x minus 2 over x minus 3. I know that its domain is x cannot equal 3, setting the denominator to 0. Intercepts. F of 0 is 0 minus 2 over 0 minus 3. That's negative 2 over negative 3. That's 2/3. So I have the point 0, 2/3. There's the point 0, 2/3. Setting the function to 0. X minus 2 over x minus 3 equals 0, which implies that x minus 2 equals 0, which implies that x equals 2. So I have the point 2, 0 as an intercept. I have a vertical asymptote at x equals 3. The function's already reduced, so I don't need to reduce it any further, and I have a vertical asymptote at x equals 3. Will there be a horizontal asymptote? Well, I have a degree 1 over degree 1, so I get a horizontal asymptote at y equals, looking at the lead coefficients, they're both 1s, at y equals 1. All right, drawing the horizontal asymptote. Will the curve ever cross the horizontal asymptote? Can x minus 2 over x minus 3 equal 1? Multiplying through by x minus 3, we get x minus 2 equals x minus 3. Subtracting the x, we get negative 2 equals negative 3, which is a contradiction. So it does not cross. Now I've got a few points here. I know the curve does not cross the horizontal asymptote, so I would expect the curve to do this, jump over the hole through the intercepts, and then trend downward following the asymptote. So now maybe just find a point or two on the other side of x equals 3. So how about g of 4? G of 4 would be 4 minus 2 over 4 minus 3. That's 2 over 1. That's 2. G of 4 is 2. And, I don't know, how about 8? How about g of 8? G of 8 would be 8 minus 2 over 8 minus 5. 8 minus 3, sorry. And so that's 6 over 5, which is 1.2. So g of 8 is 1.2. That's about here. And so there's enough, I think there's enough evidence there to show that the curve will follow the vertical asymptote downward, get close to, and pass through 4, 2, and then continue decreasing, passing through 8, 1.2, and following the horizontal asymptote and not crossing over it. Alright, so there's a sketch of the function with a hole. Alright, and let's end the section with an application. Richard and Eric have developed a liquid to apply on a car's bumper that will enable a person to remove love bugs much easier than if the liquid were not applied. The total cost for all the chemicals and spray cans is $250 plus an estimated cost of $0.75 per can per labeling. Write a linear function for the total cost C of producing X spray cans. Alright, so C of X, the cost, well, we have a fixed cost of $250 and a cost per can of 0.75. So 0.75x plus 250. Write a rational function for the average cost of producing X cans. Alright, so the average cost is the cost per can, right? The average cost is going to be a cost per can. Alright, well, let's think about that. The average cost is going to be the cost divided by the number of cans. And so then A of X is going to be 0.75x plus 250 over X. Find and interpret A of 15. A of 15 would be 0.75 by 15 plus 250 over 15. Alright, let's see, using a calculator, 0.75 by 15 plus 250, that's 261.25, that's the numerator, let's divide that by 15, so 17.42. Alright, so what does that say? The average cost of producing 15 cans is about $17.42 per can. Alright, so in a sense what's happening is, that we know it's 75 cents per can for the labeling, but that $250, that setup, is also now needing to be spread out among all of the cans that are being produced. Since we're only producing 15 cans, that $250 is only spread out so far. Find and interpret the horizontal asymptote, if it exists, for the average cost function. Alright, so the average cost function was 0.75x plus 250 over x. So now, since we have a degree 1 over a degree 1, then I would get a horizontal asymptote at y equals 0.75 over 1, so at y equals 0.75. So now what's the interpretation? Well, the horizontal asymptote tells you what happens for large values of x. Now, we can't have negative values of x in this application because x is the number of cans. But what this says is, as x approaches large numbers, as x approaches infinity, y approaches 0.75. So, what is this saying? As the number of cans produced becomes very large, the average cost per can approaches $0.75 per can. As X becomes very large, as we start producing more and more cans, the cost for the chemicals, the individual cost for the chemicals per can becomes very small, and so we just have that 0.75, that labeling cost each time. Find and interpret any vertical asymptote. Well, looking at the function, we would expect a vertical asymptote at x equals 0. Now again, we can't have negative values of 0, so if we were to consider small positive values of 0, what would happen if x was very small? Well, let's look at the graph. Let's graph this function on the calculator. So 0.75x plus 250, and divide that by x. And let's go from 0 to, I'm just going to use 9.4. And for the y's, now the average cost can't be negative, so let's use 0. And let's use a cost of, how about 300? And I'll use a scale of tens. So notice what's happening. Now we know as x becomes large, the output gets closer and closer to 0.75. But as x becomes very small, let's trace negative. Let's trace and get close to 0. So how about at 0.5? Now that doesn't make a whole lot of sense. You can't produce half of a can. The smallest number of cans you can really produce is 1. So notice if you produce 1 can, the average cost of that 1 can is $250.75. Now, if you could produce a smaller and smaller number of cans, what if you could produce 1/10 of a can? Wow, that cost would be $2,500 for that 1 can, or for that 0.1 of a can. So this is difficult to interpret because it doesn't really make sense to move left of x equals 1. But what we can say is, as the number of cans becomes smaller, right, and approaching 0, the average cost per can becomes very large. Alright, so now let's kind of turn this idea around. Here we're given a graph and we want to come up with a function that models it. So to do this, we are going to look at the information given. Asymptotes, intercepts, and just then the general form of the function. So I'm going to first focus on the asymptotes. I have a vertical asymptote at -5 and a vertical asymptote at -2. So what that tells me is I need a factor of x plus 5 and a factor of x plus 2 in the denominator. Now I'm going to focus on the intercepts. I have an x-intercept of -1 and an x-intercept of 6. So that means I need a factor of x plus 1 and a factor of x minus 6 in the numerator. So here's where I'm going to start. F of x equals x plus 1 by x minus 6 in the numerator x plus 5 by x minus 2 in the denominator. And now I'm going to say, well, there's going to be some a value here. There's going to be some maybe multiplier. Alright, so now I look at the other information. Maybe I find a point on the curve and try to make that point fit the curve. So let's see. This is a good point right here. That point right there at negative 7, 8. Looks to be a good point. So when x is negative 7, the output needs to be 8. So then I'd have 8 equals a times negative 7 plus 1 by negative 7 minus 6 over negative 7 plus 5 by negative 7 minus 2. So 8 would equal a by negative 6 by negative 13 over negative 2 by negative 9. So 8 would equal a times, let's see, negative 6 by negative 6 times 13, that's what, 78 over 18. So that means that a would equal 8 times 18 over 78. Alright, so now if I use a calculator, let's see, 8 times 18 over 78, try that again, 8 times 18 over 78, about 1.8. Alright, so putting that together, I can start by writing that my function is, let's see, I need an x plus 1 and an x minus 6 in the numerator. I need an x plus 5 and an x plus 2 in the denominator. Now, I also need a multiplier, some a value. So now, I'm going to find some point on the curve and see how well, and make it fit. So I see the point, I see a pretty good point here, negative 7, 8. Alright, so let's say then, if we have negative 7, 8, that means when x is negative 7, the output needs to be 8. So then I would have 8 equals a times negative 7 plus 1 by negative 7 minus 6 over negative 7 plus 5 by negative 7 plus 2. So 8 would equal a times negative 6 times negative 13 over negative 2 by negative 5. So 8 would equal a times 78 over 10. Now 7.8 over 10, that's 78 over 10, that's 7.8. 8 equals a times 7.8. If you divide through by this 7.8, you would find that a is about 1. Alright, so a appears to be 1, which is reasonable. So if we let a equal, and I say it's reasonable, well, let's look at this function. So if I let f of x just be equal to 1 times x plus 1 by x minus 6 over x plus 5 by x plus 2, if I multiply this out, I will have a 1x squared plus some other terms, and in the denominator I'll have a 1x squared plus some other terms. And so then I would get a horizontal asymptote at y equals 1, which I do see here. So I think this is a reasonable model for the graph. Alright, let's look at one more example, constructing an equation from the graph. And again, I'll focus first on the asymptotes and intercepts. So let's see, I have x equals negative 2 is a vertical asymptote, and x equals 4 is a vertical asymptote. So then in the denominator, I need an x plus 2 and an x minus 4. I have horizontal intercepts at -6 and -1. So in the numerator, I need an x plus 6 and an x minus 1. So I'll start my function as f of x equals a times x plus 6 by x minus 1 over x plus 2 by x minus 4. Alright, so now I'm going to maybe try and find a reasonable point. There's nothing great. This isn't too bad. This point right here is about 6, -15. That's pretty close. So let's go with that and see what happens. Alright, so I'd have -15 is a by 6 plus 6 by 6 minus 1 over 6 plus 2 by 6 minus 4. So -15 equals a times 12 by 5 over 8 by 2. -15 equals, what's that? That's a times 60 over 16. Alright, so now solving for a, we would have a is equal to -15 times 16 over 60. Alright, and I'll use the calculator at this point. Alright, so -15 times 16 over 60 is -4. Alright, so we find that a is -4. Now let's look at this for a moment. Notice that I have this horizontal asymptote at -3. So I'm thinking that the -4 is close, but I'm thinking -3 is probably a better choice. So I'm going to say that f of x is -3 times x plus 6 by x minus 1 over x plus 2 by x minus 4. Alright, so substituting that point gets you at least in the ballpark, but then you got to kind of double check with the horizontal asymptote if one exists. Now if there wasn't a horizontal asymptote to go against, I would probably just go with that a value and see how well it fits, maybe using a calculator. Alright, but I'm going to go with f of x is -3 by x plus 6 by x minus 1 over x plus 2 by x minus 4. Alright, that concludes this presentation.